Alrighty, so let's go over this. Now, to be perfectly honest, this homework assignment is one of the candidates for trimming down a little bit, so just stick with me here as we go through and not have a lot of room to show our work. So, a 1,500 kilogram car traveling at 15 meters per second to the south collides with a 4,500 kilogram truck that is initially at rest at a stoplight. The car and truck stick together and move together after the collision. Okay, this is the key here, right? Stick together and move together after the collision. This type of language is what tells you what type of collision this is and what types of equations and rules you can apply to it. If the two objects stick together and then they move together, that means that they're operating as one object, right? And then by extension, they're also going to have the same velocity. Okay, if they're moving as one object, they're going to have the same velocity. Right? So this information, this wording here is really important to understand what rules you can apply or what equations you can use when you actually go to do your calculations here. Now, what is the final velocity? What is the final velocity of the two vehicle mass? So what we have going on here is a situation in which we have one object with a certain amount of momentum that is going to be the same after. Okay? Now, I could write this, but have M1 V1 final. I could do that, right? I could do that. But what I'm going to do here is I'm going to factor out, I guess I'll just write it, M1 V1 final, M2 V2 final. What I'm going to do here is I'm actually going to factor out the V final because they're operating as one mass, the final velocity for both of them is going to be the same. And what that means is I can factor out, right? These two values right here are the same. Both of these velocities are the same. So instead, I can have this represented this way. Well, that's not initial, that should just be 1. M2. Oh, okay. And so, I guess this is not the correct way to write it. These two things are equal. Just to make that more confusing. Gosh darn it. And this. Gosh darn it. And so for both of these, for M1 and M2, I've factored out the final velocity, right? M1 plus M2, right? We've still got M1 plus M2, but I've factored out the final velocity because they're the same value, right? This final velocity is being multiplied by both of these masses. So instead of setting this up and using this for the final momentum, I'm going to use this. That's going to allow me to more simply solve for final velocity. So let's start working this. Let's see if I can mess up my notation again, which I love it when I do it. Equal to, okay, so that final velocity. Okay, boom. Oh, sorry, I'm not on the camera. So here, I'm going to solve for final velocity, right? This term right here. So I'm going to divide. Gosh, I always make that an I. It's not an I. I'm going to divide that. That's going to allow those things to cancel. And so what I'm actually going to plug in here is final velocity is equal to M1 V1 initial plus M2 V2 initial divided by M1 plus M2. Now I need to go back to the problem and plug and chug. So 15. Let's see, my masses are going to cancel out, so I'm okay to just keep those as kilograms. And that's going to be plus, what's my M2? 4,500 kilograms. And, right, because that thing was at rest. And then I'm going to divide that by the sum of the masses. So 15 kilograms plus 45 kilograms. And my calculator tells me that with two significant figures, right? Two sig figs. So with two significant figures, my final answer is going to be 3.8 meters per second south. Whoa, south. Or you can write, generally speaking, a negative 3.8 meters per second.